Remember your paying.
Okay, guys, you ready to get started? For the first hour or so, I'm going to show you another way of programming. It'll take about that long, I think, for you to really understand this. You may still not understand it when it's done. And next time, I'll show you how to create a state machine. That'll take us about a class period or two. But today, I'll show you a quick way of creating a program that works. Remember in the silo machine, we found that we could try and program it with the truth table, but that didn't work because the outputs had to depend on more than just the current state of the inputs. Remember, there was the case where in the silo simulator, bring it up. There was the case in the, by the way, whoever told me you can turn off Merlin, thank you. That is so nice. Okay, remember there's the case where the box comes along and it's empty, and so it triggers the prox sensor but not the level sensor, so we try to fill it. And then as it continues to move on, we end up with this case where the prox sensor is triggered. We have a full box, but the level sensor is not triggered because the level sensor is not over the box. Now, of course, you might say, well, you can solve the problem mechanically because you should move the level sensor over a little bit. Okay, that may be true. Maybe it's true that you should align those two a little bit better. You could say, well, how about if we use a timer so that after the level sensor goes off for a certain amount of time, well, then we're not going to turn on the cylinder valve, we're just going to keep the motor on. Well, that's what I would call a dirty program. Because you've got a level sensor right here, you've got a prox sensor, you should use that information and remember that information in order to solve this problem. Okay, well, we can add another level sensor. Yeah, that's true, but that's more expensive. Bits in the processor or in the PLC that we already have are cheaper than a new sensor. So try selling that one to your boss. Anyway, and you may be able to sell it actually, because sometimes the goal is just to get the project done. Who cares what it is? The point here is commonly you can fix things in hardware, you can fix them in software, you can fix them electronically. Okay? It depends on what your constraints are as to which one you choose. But I want you to really master PLC programming, and so it's important for you to learn how to remember that events have occurred using a bit like I did, so that you can make your system work, so that you learn how to fix it in software. Anyway, so the point was that remembering an event is important. Now there are multiple ways to remember events, and the idea here is that basically your program, envision your program here, the outputs need to depend on more than just the current state of the inputs. Your outputs needs to be a function of inputs that are current and past inputs. Does that make sense? So in other words, your program has to have memory and remember what the past inputs look like. For example, what we need to remember here is that prox and level were both true at one point in time. So we need to remember that there was a full box. Okay? There are multiple ways of doing that. I showed you how to use a bit to seal in a memory bit, basically, once those two go true. And remember that we had a full box at some point. I'm going to show you another way to do it, but I'm going to start off by demonstrating it with the I/O simulator. There's a program that you can download and you're welcome to use. It's in the fall 2015 folder, and I call it the sequence machine template, because this program uses what are called sequencing instructions. I'll show you what they are and how they work. But you are welcome to use this program just as it is. Let me show you what it looks like. We'll open up here in a moment. You're still thinking? There we go. All right. Now, you don't really have to make a whole lot of changes to this program for it to work. It looks fairly complicated. It's really not once you understand it. There's a bunch of instructions down here that you really don't even need. It's a total of 6 lines long, and you can use this as a template to solve a lot of programming problems. Okay? I'll describe how it works in a moment, and I'll demonstrate it for you and all that. But let's look at each of these one at a time. The two main instructions here to understand are the sequence compare and the sequence output. Now let's think about this for just a minute. Hopefully all of you have a washing machine at home, or at least access to one so that your clothes are clean, right? Well, we're engineers, so that may be a big assumption. Anyway, your washing machine. Have you ever noticed there are multiple different settings you can go through, or programs you can go through? So you might use delicates for your dress clothes. You might use hard, heavy wash for your work clothes. What's the difference between those? Well, basically, your washing machine has a set of inputs and outputs. Now, I'm just going to concentrate on the outputs because that's the most important part for a washing machine cycle, or even a dishwasher. You might have a spin output that goes to the motor. When you energize it, it causes it to spin. Why would you use that? You use that to basically drain water out of the clothes. You might have a hot water valve, a cold water valve. These are two different valves, right? Some of the cycles include hot water wash, some cold water wash. And depending on what you need, you select it appropriately. What else do you have? Well, there's the agitate. Now, how do you spell agitate? A-G-I-T-A-T-A-E, is that right? Without the D? Agitate. I can never remember. So I'm glad there's spell checker errors. Word process. Anyway, so you've got agitate. What is agitate? Well, basically, spins the tub a little bit and basically just moves the agitator in the center back and forth, which causes the clothes to kind of turn around and be rubbed together to try and get the dirt out. What other outputs might there be on the washing machine? What? An output would be like input would be things like the water level being sensed or the door being open so you can take a condition. I can't think of any others. I'm sure there's some others. What's that? The lid lock. Well, that's an input. I'm trying to think of outputs. Oh, I see a lock for the lid so that it can't be open. Okay. Yeah, that might be one. Thank you. Okay, so lid or door lock. Let's just call it a hatch lock because some washing machines are front loading, some are top loading. I learned something the other day. I was thinking of getting a front loading washing machine, and I talked to some people to repair them, and they said, don't do it. It's top loaded. I don't know. They said it does a better job than it's got before arrived. I looked at the price tag and looked at the cost of parts for fixing my washing machine because it was broken versus buying a front loader. I fixed my washing machine. Very significantly expensive. All right, so anyway, so what is the difference between the programs that you run? Well, it's basically how long each of these things are on, right? There might be a time sequence. So let's see, how can I draw this? Let's just put them across this way. So we've got all of the different outputs. If this is a time axis, then maybe the cold valve has to be on for a certain amount of time. Of course, I know there's really a sensor that sort of shuts off after the sensor goes off. Well, let's just pretend for the moment we just have a dumb washing machine with no inputs. So you turn on the cold valve for a certain amount of time in order to fill the machine. Okay, and then what? Well, then you might agitate for a certain amount of time to try to get the clothes clean. What else? Well, then you probably spin out the dirty water, and then you might turn on the hot valve for a certain amount of time. And I shouldn't have made my line so long. Let's see, spin. We're going to spin afterwards. And then we're going to add some more water, the cold valve, and then we might, oh, I forgot an important element, that's the pump. Because it's important to pump out the water, right? And as you're spinning it, you also have to turn the pump on. So let's see, pump will be on here. And so on. So you get the idea. Basically, it's just a sequence of outputs that are on for a certain amount of time. Now, a different program might have a different agitate cycle. Let's say that you wanted the delicates. Well, on my washing machine, the way it worked is agitate basically is on for a very short duration of time. Instead of being on continuously, it agitates for just a moment and rests. Agitates for a moment. That gives the clothes a chance to separate out because basically it's squishing them together, it's turning them over. So that gives it a chance for the clothes to rest and sort of relax and not be squished together quite so hard because it's not continuously. Now, since I'm breaking up the cycle, I'm going to move my dash around. The line was there just to align all of these so you can see what they want, or what they are. Okay, so eventually we get to the point where we spin the thing for a long time, we pump all the water out, and the cycle is complete. But essentially this is a recipe, right? Each one of the settings that you have are a recipe of outputs that turn on in sequence and wash your clothes. Well, that's what the sequence output instruction is like. Now, the sequence output instruction has to have a list in memory somewhere of which outputs you want on, okay? Because basically, what this thing does is it can turn on any of the outputs all at once that you want. Notice it's referencing output word 6. This is not referencing one particular bit. This instruction is able to turn on or off as many outputs as are in that word. So it can turn on or off 16 different outputs. Okay? Now there's many ways of using this instruction. I have this instruction hooked up with a sequence compare instruction so that once sequence compare says go, then this moves to the next set of outputs. So you can think of this as being broken up in memory into integer time steps. Does that make sense? And to stick with my integer time steps, I'll have to break this up a little more. So basically for 1, 2, 3, 4, 5, 6 time steps, we're going to have the cold valve on. And maybe if this is the hand wash, nominally hand wash cycle, then we'd have agitate on for a time step, then a rest time step, then on for a time step, then a rest, and then continue. And so we're going to break up the outputs in time. Okay. So what I have to do is somehow program all of this into memory. I have to have ones here, zeros everywhere else for the other outputs, and 1 here, 0, so on and so forth until I get to here. And what's nice about this, it's rare that we have the pump, or we have 2 outputs on once, but it does happen. For example, in the spin cycle, the pump has to be on, okay, so that we can pump water out as it gets wrung out of the clothes. Okay. But what this instruction will do, we'll put a pattern in memory of outputs, how we want them to be triggered, and this sequence output will just move from one line to the next as we tell it to. It keeps track of what line it's on, and as you trigger it and tell it to move to the next, it goes to the next and sets the outputs just as you have in memory. Okay? Does that make sense? So this basically runs through the list and puts them out on the outputs. And it's referencing output 6. Now what is all the other stuff? Well, the list has to be in memory somewhere, and this address simply points to the memory where the pattern that you want the output is located. So this particular list is in B3:10. If you guys have Logic Scroll open, you can actually open this program. I have it posted, like I said, in fall 2013. And it may help you to see it on your screen as well. Now the length here, that's another thing that has to be set. The length is basically how many steps there are in your list. This particular list has 8 steps in it. There are 8 different output patterns that are set, 8 different words, okay, that set the outputs or unset them. Because this, basically what this instruction does is every time you trigger it, it looks in memory at its current position and copies that memory to the output word. Does that make sense? So go to memory, and whatever position it's at. Right now it's at position 0. So go to this address, it'll grab the word that's at that address and put it into the output. And then when you tell it to increment and the position increases by 1, then it goes to the following address just after this, grabs that whole word, copies it to the output. So it's more of a copy-paste type of instruction that moves through the list. Now what else is there in this instruction? Well, there's a control register. You don't have to worry about this too much. You just have to give it a word in memory somewhere in the controls registers file, hopefully, so that it has a place to remember how long is the list, where is the list located, what position are we in the list at this current time, whatever that time happens to be. And then there's this thing called mask. Now I'll explain the mask just a little later, because that one may be a little bit confusing. But let me go ahead and show you the list in memory. In memory, the list is stored in the binary file. So if you go to the binary file and look at address 10. Now address 10 is blank. There's nothing there. Here's something that can be a little bit confusing. In the sequence output instruction, there is an extra beginning step that is only set to the output once. Now, for our purposes, we're not going to worry about that. We're not going to worry about what's in there. You can just leave it blank. But there are reasons for using this. I don't want to go into them right now. Essentially, the list starts at the address after the one you reference. Okay? So what you really care about is the address just beyond the address that you type in there. So we're interested in 11 through 8 steps. So 1, 2, 3, 4, 5, 6, 7, 8. All of these are my list. And these are what I've put in that I wanted to output. So in the first step, what it's going to do is it's going to copy B3:11. It's going to copy all of these bits, all 16 of them, and it's going to paste them into output 6. Okay, now output 6, if you look in this particular simulator, output 6 is this output right here. So it's going to copy all zeros and their 1, which is right here, to output 6. So in the first step, what is it going to do? Well, it's basically going to turn on the 0th bit right there, and it's going to turn off all of these bits because there are all zeros here. So simply copies that, pastes it there. And then when I trigger that instruction to go to the next step, then it will copy this line. So it'll turn off this one and turn on this one, essentially. That's what it looks like. But really what it's doing is it's turning off all of them and turning on this one. Next thing it'll do is it'll turn on both the lower bits. It'll turn on bit 0 and bit 1, and so on. Now what that's going to do is drive this display to count up. Because notice all I did was I counted in binary. 0, 1, 2, 3, 4, 5, 6, 7, 8. So what's going to happen is this display, as I trigger that instruction over and over again, this display is going to count 1, 2, 3, 4, 5, 6, 7, 8. Okay? Now there's more to this program than just that. I could set it up so that I had a timer running. Remember how we worked in the traffic light simulator? And we used one timer that self-restarted. We compared the value in the accumulation so that we could turn on the lights. Well, we could set up a timer like that and have that timer, when it's done, trigger the sequence output instruction. And we simply move, you know, with whatever that time frequency is or that time period is, it would set the outputs in sequence. And you'd see 1, 2, 3, 4, all the way up to 8. But I've got it set up a little more complicated than that, because there are a lot of times where what you want to have happen is a process that is recursive. It happens over and over and over again. For example, any industrial process where you're manufacturing something, like, for example, putting candy in a bag. Okay? There's going to be bag after bag after bag after bag filled with candy, right? And you essentially want to do the same process over and over again. But a lot of times, you can't just base it on time. You can't just say, once so many seconds have elapsed, I'm going to assume there's another bag in place that I can fill with candy. Okay, you can't do that. You have to sense that the bag is actually in position. There's probably a lot of other requirements before you try to fill the bag with candy. So that's where the sequence compare instruction comes in. I don't want to just look at one input. I may need to look at multiple inputs. I may need to know that there's a bag in place. I need to know that there's enough weight of candy to fill that bag appropriately so that we don't jip our customers. I may need to know that the bag is open and not closed. Okay, so I may have sensors for all this, so there are multiple inputs I have to look at before I go to the next step where I fill the bag with candy. Does that make sense? So there are sequences that have to happen over and over where you have to look at a bunch of inputs, see what they're doing, make sure they're in the right order, and then set a bunch of outputs. And then go back and look for the next set of inputs. The next set of inputs, after you've opened the bag and you're filling the bag, maybe is the bag full? So there's a sensor that detects when the bag is full, and then you need to move on to the next step of closing the bag. Now I've set this program up fairly simply. Now when you download this, you won't have to change anything. You don't have to change any of these instructions. They all just work. What you have to change are the patterns in memory. So let me demonstrate how this works, and then I'll explain it. Now, I'll put a comment at the top of the program to describe what you have to enter to get it to advance. Let me describe the sequence. Let me describe the sequence compare instruction next, because what this does is kind of the opposite of what this does. This instruction looks at all the inputs on whatever address you tell it to look at. I told it to look at address 5, which is right here. So I'm going to put inputs in here. So it's going to look at all of those inputs, all 16 bits, and what it's going to do is compare the inputs to what I have in memory at this address, but also in a list. So I have another list in memory that represents the input patterns I want to see before that instruction finds a match. So what I want to see is bit 0 come on, then I want to see bit 4 come on, then I want to see bit 8 come on. You see how these are only changing by 1 bit? I want to see bit 12. Now, it doesn't have to be that way. Okay, we could set it up so that a bunch of inputs change. But basically, this instruction is going to look at input 5, and it's going to constantly be looking for this, for what's at address 1. It's going to look for that pattern. Until it sees that pattern, it will not trigger sequence output to change to the next step. But once it finds the pattern, then it'll trigger, basically it'll find to be true for one cycle. It will cause the sequence output to go to the next step and set the outputs according to whatever's next in memory. And then what this instruction will do is it will immediately go to the next line. It'll load this and start looking or waiting for input 5 to match that line, because that's the next line in the list. So let me demonstrate it, and we'll see how it works. All right. Download, run. Okay, what is it looking for first? It wants to see the inputs look like this. It wants to see bit 0 come on in input 5. So let's do it. Turn bit 0 on. Well, we'll increment this. So there it is. Came on. Oh, well, I forgot there's one thing I added. I added a start-stop circuit, so we have to tell it to run. So we've got a stop button here and a start button here, so like normal. Now I'll do that. Now it's energized. Now it's actually looking. That's why I've got the run on here. These instructions weren't doing anything because I didn't have the system input. Anyway, now let's increment this. So it's looking for input 5. This instruction is looking for input 5 to look like this. It wants to see this bit right here on. When I increment that wheel, that comes on. So what does it do? Well, it takes sequence output, or tells sequence output to go to the next step. Sequence output hadn't done anything yet. But now that it's been triggered, sequence output copied B3:11 to output 6. Now notice there's a 1 there, so it put a 1 in place. Okay. Now, what do you suppose that sequence compare is looking for next? I'll give you a hint. It's in position 2. It's looking for the next step in the list. So which memory address is it looking at to compare I5 to? You're all lost at this point because there's no answers. What questions do you have? Any questions so far? Well, let me demonstrate it a little bit more. Maybe you'll catch on. What it's looking for is this bit pattern. It sees that this 1 is on, so it said, I found it, it jumped to the next line, and now it's waiting for this bit to come on. It's waiting for bit 4 to come on. The way I can turn bit 4 on is by incrementing the next one. Okay, I put a note in here so I'll remember what to do. Plug in 0000, 0001, 011, 0111, and so on. Okay. So let's turn on the next location. It's looking for this. Okay. So now I have a bit pattern that matches. Look in memory, you'll see what I'm saying. The bit pattern is 10001. That's exactly what I have here. Once it finds that, it says, okay, I found it. It turns on its find bit. It jumps and goes to the next position. Now it's looking for this bit pattern on the inputs. And when it's found, that causes the sequence output to go to the next step in the list and display what it has in its list, which is B3:12. That's why I turned off bit 0 and turned on bit 1, because that's exactly what this word says to do. Does that make any sense? It's starting to make more sense now? Yes, sir.
Do we could go backwards?
No, you cannot make it go backwards without writing to the memory address directories. You can make it go backwards, but you have to be really tricky. It turns out that you can, if you go to the registers file, and you know what you're doing, I'm not sure that I would. The control registers are at 0 for the sequence compare, and at 10, that's just where I happen to assign them. So 0 for the compare, 10 for the output. If I were to manually write the position word here as 1 instead of 2, it would go backwards. But you have to be tricky because you'd have to write a 0 in there, have it increment so that it actually goes to position 1. Because just writing its current position there won't cause it to change the output. The low to high transition on the run before the instruction. Okay? It's the low to high transition right here that causes it to actually go and set the outputs. So it would be tricky and messy.
You'd have to do the sequence compare. You'd have to change that, then activate the sequence compare and get it.
Yeah, well, the sequence compare, the only reason the sequence compare is tied to the sequence output is because of the code I put in between. Okay.
I'm not working.
Okay, you have to hit the start button, change the, hit the start button, there you go. And now,
Mine's not working either, I've used the
Sorry?
start button.
you use the start button, it is your PLC in run mode.
Yeah.
Mine doesn't work either. I ran through all of them and it finally started working.
Okay, well, what's happened here, okay, let me describe this. What's happened with this sequencer, and this happens sometimes, is that the position, notice that as I'm going through this, the position of sequence compare is 1 ahead of sequence output. If these two get out of phase, which can happen, he's got a 5 here and a 0 here. When that happens, it won't work. Okay? So sequence machines like this are really easy to break. So it's common to have a reset button. I haven't programmed that in here. I was going to show you that a little bit later. Okay, but there is a way to reset it so that both just start back over at the beginning of the sequence. For example, let's say we were using a sequence machine on the silo simulator. Silo simulator goes along. For some reason, the box comes underneath the hopper. We overfill the box, or the box falls apart or something. We got an emergency, hit the stop button. In that case, you need a reset button so that the sequence would start back over at the beginning of getting a fresh box to fill. Does that make sense? And so you need a way of resetting both the sequence compare and the sequence output, and it's very common to have a reset button for that purpose. Okay? All right, so let's continue through this and see what happens. Basically, I've written in information here so I didn't have to go into memory to look at the bit patterns. But basically, the next thing to do is just turn on this one. That causes the count to increment. Next, I need a 1111. That causes the count to increment. I need a 1112. Increments again. 1122 and 1222. That's the end of my sequence. Notice that all I did is I went to 0007. If you look at memory, the binary file, I want to look at it in binary. There is one more step in the sequence. The sequence output has the opportunity to turn on bit 3, which is right here, and turn off the other bits. That would put an 8 here in the display. So what do I have to do that? Well, let's find out. Incrementing this causes it because the next pattern that sequence compare was looking for was 001, 0001, 0001, 3 zeros again, 1, 0. That's exactly what I have now. 001, 3 zeros, 1, 3 zeros, 1, 3 zeros, 1, and a 0. So I was looking for that last bit pattern, and I didn't have room to add that in it. Kind of makes sense. Now what? Well, we'd like for there to be a way for the sequence to start back over. Okay, in fact, there is. We take this back down, and you'll notice that it starts back over because what's happened is I took this back to the very first thing the sequence compare was looking for. I took it back to this. And I went past it and I went all the way to 4 zeros. But what happened is sequence compare, I set it up so that it starts all over. Starts at the beginning. So it's looking at the beginning of the list, and it was looking for this, and and it found it, because you see what happens is these instructions automatically start back over. So when it first starts, it starts from this unused word, because it's looking for the next set. Okay? But when it repeats, however long your sequence is, it comes back and looks for this word instead of the one word again. Okay, so anyway, here's what you really need to know. This address, the one that follows it, and the one follows it is where you really should start. That's what you really need to know. Now I'm going to show you one more thing about this program, because you notice I've got all this data in memory, and all this data is arbitrary. I can make it do anything we want. Okay, let me prove that to you. I am going to change the bit patterns in memory. I'm going to basically just flip them around. I'm going to make it count backwards. Okay, so put a 1 here, put a 0 here, 1, 1, 1. Let's see, let me think 1. I got to choose 1, 0. And then 1, 0, 0 is right. I'm going to cheat the clock here. It's going to be 1, 0, 0. And I'm missing one. What did I do wrong? Let's see. 1, 1, 0, 1, 1, 1, 0, 0. And that should be 1. So that's what I put. Okay, 1, 0, 1, 1, 1, 0, and 1, 1, 1, and 1, 3, 0. Now watch what happens. It has not updated the display to give me an 8 here. The reason it has not updated the display is because sequence output has not been triggered. But when I trigger it, it's going to move to the next step, which will not be an 8, it will be a 7. Because what I did is I put a 7 essentially in memory here. Let me show it to you. And let's see, that's what I want, but I want to view it as this. Okay, so this 7 is what it copied over into here. Now as I increment, it's going to be put a 6, 5, 4, 3, 2, 1, because all of this is arbitrary. I can make it do whatever I want just by changing the pattern in memory. So you get the idea that the pattern in memory is pretty important. You have to design that pattern, and you have to put it in memory. How do you do that? Well, you can come in and you can set the bits manually if you want to, but you don't have to. What you can do is have a section in your program. I'm going to turn my program off. You can have a section in your program that will move the data into memory. These instructions here are move instructions. Move is not a really good name for them because they're more copy instructions than they are move. They don't take something from somewhere and move it somewhere else. They take a copy and put it in memory somewhere else. Okay? And these are a little bit more advanced than just a move instruction like I showed you before. You may remember we used a move instruction once. Anyway, it's essentially a copy instruction, but this is a masked move. It's not exactly a move instruction. To understand what a masked move is, you need to understand the concept of a mask. Let's say that we were dealing with, in fact, let me go ahead and describe it in the context of the sequence compare and the sequence output instructions. Remember that the sequence compare and the sequence output instructions are dealing with whole words of data, either a whole word of input data at address 5, 16 bits, or a whole word of output data at address 6. Okay? Now, it may turn out that you want to look at inputs, but you don't really care about some of the inputs. There's only 2 or 3 in there that you really care about. Okay? Maybe you've got a PLC where you've only got 1 input card, you've got 16 inputs. There's only 2 or 3 of them that actually drive the sequence. Okay? In that case, what you can do is use what's called a mask. And what the mask does, I doubt the METs know this. How many people know what an AND instruction is? Okay, you know the concept of an AND? Okay. Well, do you know what a bit? How many people know what a bitwise AND is? Okay, well, bitwise AND is essentially, I'll have to describe this because the bulk of the class does not know. A bitwise AND, hopefully works better than this eraser. I think this whiteboard has seen better days. Okay, a bitwise AND works like this. If you have, let's just take an 8-bit word. Okay, so 0, 1, 0, 1. Give me zeros and ones at random. I don't care. What do you have? 1, 0, 0. I heard a whisper of 1, 0. What else? can speak up, this is a two-way conversation.
Good one.
A 1, okay, what else? I'll make it interesting. 1, 0, 1, 1, 0, 0, 0, 1. Okay. A bitwise AND is calculated this way. Now notice I don't have a plus here. AND is a logical operation that is different than plus. Okay. AND is like a switch. I haven't described this yet. I should describe it for the sake of the AND is like this. If switch A and switch B are true, in other words, if they're both on passing power, then the output, let's call it Y, could be on. Okay, so to make the ECETs happy, let's put L1 here, and let's connect this back to neutral. Okay. All right. So basically, switch A and switch B has to be on for Y to be true. Now, the other option, another way we could wire this up, is to wire it up in an OR configuration, so that if switch A or switch B is on, then the output would be on. So a bitwise AND, basically the truth table for an AND instruction is like this. A, B, output Y. The only possible combinations are these. We don't have any other possible combinations. But both A and B must be on for the output to be on, otherwise the output is off. So that's a logical AND. A logical OR truth table looks like this. OR over here. A, B, Y. Only possible combinations of inputs are the same as they were before. But OR says if either one is on, then the output is on. But A, B, neither one is on, so the output's off. And the rest, we have at least one input on, so the output is. Okay? So that's logical OR. If we perform a bitwise AND, then what we're saying is bit by bit, okay, each individual column, and them together. So what is 1 and 1? Don't answer 2, right? This is a logical operation. It is 1. What is 0 and 0? 0. 0 and 0 again is 0. How about 1 and 0? 0, 0. So basically what you see is the only time we will get a 1 is when we have a 1 in both places. So this is the logical AND bitwise operation. Okay? Now how would we use that in the context of a mask? Well, let's just say that on input 5, I am only interested in bits 0, bit, let's see, 3, bit 4, and bit 6, because I happen to have sensors that I'm interested in for driving the cycle on bits, hooked up to bits 0, 3, 4, and 6. Those are the only bits I'm really interested in. Now, it's possible that other inputs could be on or off, but I don't care about the other bits. Okay? I don't care about bit 7, bit 5, bit 2, or bit 1. All I care about are bits 6, 4, 3, and 0. Well, if I have a word in memory, let's put an integer in here. So an integer in memory location 0, I could say put a 0 here, a 1 here, a 0 here, a 1 here, a 1, 0, 0, 1. And what we will do is the mask will be applied every time either sequence compare or sequence output is running, whichever one it's associated with. And what it'll do is it will always take the input word that I've specified, let's take compare for example, and before it looks at it, before it tries to compare it with what's in memory, it will AND what it sees on that input word with the mask that I've told it to mask. Does that make sense? So it will perform an AND. What that will do, AND is really good at forcing things to go off or to turn off. Now, just for example, let's say that we have a 0 here as an input, and let's have a 0 here as an input. Okay, so sensor 6, which I'm interested in, is on. Sensor 4 and 3, which I'm interested in, are both off. Sensor 0, which I'm interested in, is on. Okay. Now, the mask here will AND, so 1 and 1 are 1. 0 and 0 are 0. 1 and 0 are 0. 0 and 1 are 0. 0, 0, 1, 0. And so all that will effectively pass through the mask, the only ones that can pass through are inputs that I'm interested in. Does that make sense? everything else will be forced off. Yes.
So if you had, like on line 2 or line 1, if you had 1, 1, would it still be 0 on the output? On line 2?
Here?
No, sorry, from the right, going in.
Well, here, draw what you want. I don't understand. I'm a very informal teacher. I'm glad you guys come up and show me what you're talking about. This is a good question.
These are both on.
Yeah. Good question. Yes. The question is, if these are both on, would this one be on? Yes, it would. But remember that this bit represents an input I'm not interested in. So I would never put a 1 in the mask. I would put a 0 here and force that to go to 0, because then I always know that this will be a 0, I know that this will be a 0, and I know that these two will be a 0. Does that make sense? I know they will be zeros because, look, I put zeros in the mask, and that will force those to be off. And then, when I want to go and compare this to what's in memory, I'll just make sure that in the memory location, I have set those bits off. Does that make sense?
Okay.
So that part will always match. In other words, I will effectively ignore all the inputs except the ones that I'm allowing to get through by the mask. Okay? Any questions on that? So that's the idea of a mask. And a mask is a general concept that's really important to understand because these are masked moves. I may want to write data into memory and not overwrite certain bits. There may be only certain bits that I want to write. So you can put a mask in here so that only certain bits would be forced on. The others would be unchanged. Okay? So, for example, let's say I want to use a move instruction to copy data . Let's just say, for the sake of, in fact, here, let's make a real quick program. I'm going to make a quick program to move some data around. I'm going to use a mask move instruction. All right, so let's grab the mask move. Let's see. Keep the mask. There we go. Grab a mask move. The source is going to be very simple. It's going to be all of the bits on input word 1. So I'm basically going to take the status of all these switches. I'm going to mask it. Let's see, I'm going to make it ignore some of the switches. Which switches do you want me to make it ignore? How about if we just ignore all of the odd numbers? The 1, the 3, the 5, the 7, and so on. Okay. So the mask that I would use would look like this. It's most significant bit always to least significant bit. And so it would be ignoring all odds, so a 0 for the 15th bit, a 1 for 14, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So I'm not going to ignore the 0. I'm not going to ignore the 2. I'm not going to ignore the 4, but everything in between I'm ignoring. Does that make sense? So that's the mask that I want to get. Now let's type in that mask. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. I'm going to put B for binary. And it doesn't like it. Sometimes it likes it, sometimes it doesn't. So, try this differently. With a calculator. Do you programmer? Now in binary, let's try again. 0, 1, 0, 1, 0, 1, 0, 1. Remember, it eliminates leading zeros. That's why there's not a 0 at the beginning. Okay? 0, 1, 0, 1, 0, 1, 0, 1. If you look closely, you'll notice that I actually do have a leading 0 here. Okay? So the 0's position will not be ignored. The 1's will, the 2's will not, all the way up to the 15's position being ignored, but the 14's position not ignored. Now let's change this to something that Logix Pro will accept. Let's go to decimal. It's 21/8. 45. So mask is 21/8 45, and it likes that. Notice it's 5555 in hex. Let's find out if that's true. Yeah, sure enough it is. In binary, once again, that's what it is. The destination will be just the lights. Okay, so let's put this out on 2. Let's download this and run it. Basically, every time we go through this, the rung preceding the or the instructions preceding the instruction are true, so this is going to happen every time it goes through the scan. Okay? So notice, well here, let me change this. Okay, now, if I turn on any odd input, it does not transfer that through. But if I turn on any even input, that gets copied over. See, because of the mask. Do masks make sense now? Okay, so that's what a mask is. Now let me go back and open up the other program. So your job is essentially pretty small if you use this program. All you have to decide is how many steps you want your sequence. You got to enter that here and here. And then you have to decide what input word and what output word you want it to work with. And then you have to decide what your list should look like. And then, ideally, you would put your lists into these move instructions rather than going in and manually entering the data in the binary file. If you don't want to do that, you don't have to. You can simply eliminate rung 5 by deleting it. You could eliminate rung 6 by deleting it. But I've set these up, I probably should have commented it, but I've set these up to transfer information into memory so that the memory will be overwritten and the data will be appropriate for what I wanted the program to do. But anyway, let's analyze these one by one. This first mask move instruction, in fact, the entire rung here, which has multiple outputs, which are multiple move commands, this rung sets all of the list that's associated with the sequence output instruction. Because notice the addresses are B3:11, 12, 13, all the way to B3:18. Okay? So what's going on here is we're taking a constant number, using a mask, and putting that number in the destination. Now, I didn't want to affect certain bits. In fact, let's find out what mask I used. So if we take 15 in decimal and go to binary, what I used was a mask of 1111. In other words, the only bits that I want to affect in this word are the lower 4 bits, the lower nibble. Okay, the least significant nibble is the only one that I want to affect. And so if you look in memory, sure enough, B3:11, the only bits I ever affected were the lower 4. You see that? All the way from 11 through 18, all I've done is use the lower 4 bits. Why do I want to do that? Well, that leaves these other bits available if I want to use them. A lot of times you end up running out of memory in your programs because you have so many things that you need to remember or that you need to put in memory. So this is just a way where I can salvage these other bits and reuse them if I want to. Anyway, so what does this instruction do? Well, it puts a decimal 1, which also happens to be a binary 1, into word 11. So sure enough, there it is. What does this instruction do? It puts a decimal 2 into address 12. Well, address 12 has a 10, which in fact has value 2. Does that make sense? Because the 2's place is on, the 1's place is off. So on and so forth. Then we put a 3 into the next memory location, a 1, 1. What number do you expect to see when I scroll down to the next masked move? 4, because the 4's position is off. Does that make sense? And so that's exactly what we've got. Now, the input list is a little more complicated. Notice I wanted to work with the entire range of bits. And so instead of having a mask of 15, I use a mask of 65535. Now that mask looks like this. The mask is everything on. In other words, I'm going to deal with all of the bits in that word. Okay? And I have to, because notice the sequence that I wanted to see had to do with all these. All these numbers together represent a pattern. Okay?
I have a question.
Sure, please.
That OSR operation, what's that?
I was about to describe that. OSR is a one-shot rising. It's kind of misnamed. Basically, I only need to put this data in memory once. Once the program runs, once it starts running, I just want the data copied. I don't want to waste scan time with this every time I go through. So the OSR instruction is a set of contexts that reference a bit in memory. You have to decide what bit you want. And what it does is it goes and looks at that bit in memory. If that bit is on, it does not execute this. It just skips it and goes to the next one. It's called a one-shot rising. Basically what it does is if it comes to this address and it goes to memory and sees that this bit is not on, it will turn it on and then execute all of this. That way it only happens once. Essentially, you can use it to make something happen once. So I put that in front of both sets of instructions. Notice I had to reference two different bits. If I reference the same bit, what would happen is it would come to this line, the PLC would see that this bit is off, it would turn the bit on and perform this. Then it would go to the next line, and if I use this same bit, it would look, see the bit's on, and not do anything. Okay. Now another way to get around that is I could have put more ORs and put all the input stuff on the same line, but I was trying to keep them separate. Are you thoroughly confused about sequences?
I have one other question.
Yes.
I see that you masked the inputs there.
The 15 here?
Yeah. Was that just for demonstration purposes, or?
Yeah, that was so I could tell you what masks are. Basically, it will ignore, now be careful, this is not the inputs, these are the outputs. Because B311 through B318 are associated with the output instruction. So what I'm doing is I'm masking off all of these other outputs except for the low nibble. And you remember that the only number that changed was this low number. Now we can explore the masks for the sequence compare and sequence output. Not surprisingly, they match the data in memory exactly. F is 15, where its lower nibble is on. So what that does is that forces the sequence output to only affect these lower bits. And you might think, well, that's duplication. How come you did that in the mask move and you did it here? Well, in the mask move, what I'm doing is I'm simply putting the data into memory, in the binary file. So I'm preventing the mask moves from affecting anything else in the binary file. This instruction grabs data from the binary file and puts it into the outputs. Okay? So this is masking and preventing me from writing anything into these outputs, which is a totally different place than the data in memory, which is in the binary file. Okay? Does that make any sense? I'm sure you'll have questions. This is a complicated machine. It's not real straightforward. But what I'd like to have you guys do, and I have you do this in the homework, is to program the silo simulator using this sequence machine. So before I have you do that, I'm going to do it myself so that hopefully you'll understand this a little bit. It will actually only take us a few minutes. Once you understand this, it's a very quick and easy way to program. So I'm going to go into the silo simulator. I'm going to check a few things. I want my start and stop buttons to work. Let's check the addresses and make sure they're correct. The start button is, that's the right address. Stop button, that works. But the run on, where is that? Well, that's actually over here. I'd rather use the white. So the address is a little different, which means that I also need to change these. Does that make sense? This is a different simulator, so I've got to change where some of the input and output addresses are located. Now my start and stop button should work and should start and stop the cycle. Okay, I'm going to get rid of this comment, or actually this whole run, because that's no longer the sequence I'm interested in. Now let's consider how many steps we need. What do we want to have happen? One thing that's kind of nice is if you make a list of what needs, in fact, you know what, let's go into Excel and let's make it there. That'll keep it clean. What I like to do is make a list of what the input should do and what the output should respond. Go into Excel and let's do that. Now in the silo simulator, how many inputs are associated with the cycle that goes over and over again? What all was there? How many inputs deal with fill-in box over and over again? Prox and level, there's only two, right? Prox and level are the only inputs involved in filling boxes over and over again. How many outputs are involved in filling boxes over and over again? Still just two, right? Because solenoid valve and motor. Now you can say, well, what about the fill and full? Well, we can take care of those later. Okay? They're not really an integral part of the process. If I was to change fill and full, that doesn't change what happens in the mechanical system, right? The only thing that makes something happen in the mechanical system that gets boxes to keep coming and keep filling is the valve and the motor, okay? So all I'm really interested in are prox, level, motor, and valve. Those are the core of the cycle. So, inputs, and I'll post this spreadsheet for you. You can copy it if you like, but I will post it for you. Outputs. Okay, what inputs do I have? Prox and level. Outputs, motor and val. Okay? Now, I like to start with inputs. Is that right? Yeah, I like to start with inputs. That makes it work well. Because we're looking at sequence compare. You can do it one way or the other, but this is the way that makes sense to me. We're looking at sequence compare, we're looking at inputs first to trigger the outputs to go. Okay? So what do we want to see? Well, we want to see that there's no box in place, that it's not full. All right? That's what we're looking for. When we see that, what should we do? Let's go back and look at the system. When we see that there's no box in place and level's not true, what do we want to do? What output should we turn on? Should we turn on valve? No. So that's the response. We're beginning to generate both lists. This will end up being the inputs list that we look for. This will be the outputs list that is set in response to finding this input. When we find this, we want to set this. Make sense? Okay, what happens next? Well, in the mechanical system, what's going to happen after PLCs have been in a long period of time is that the level will not be true, but prox will be true because the box will come into place. So prox true, level not true is the next set of inputs that we're looking for. That's the next step in our sequence. When that happens, what do we want to do? We want to turn the motor off and turn the valve on because we have a box in place that's empty that needs to be filled. What would you expect to see happen next? A full box. Right? Because eventually we'll get to the point where both of those are true. Let me go to that. Okay? At that point, what should we do? Turn on the motor, turn off the valve. What would we see happen next?
Level false, prox.
That's one option. Another option is prox true, level not true. Now, let me warn you, this is an unnecessary step. Okay, we don't have to have this in our sequence because the outputs don't change. You see that? Anytime you see inputs change, but outputs not change as a result, it's unnecessary to have that step. We can leave it in, it doesn't matter, it won't hurt anything. Okay? Really what we're looking for is no box and no level. Right? That's what we really want to find. But I'll go ahead and program it this way so that we will have 4 steps in our program. Notice all I've done here is I have created an input list and a response output list. But we have to be a little careful here. Another thing I like to do is put in the addresses. Prox is on input 1/3. Level is on input 1/4. Motor is on output 2/0. And valve is on output 2/1. Okay? We have to be careful. One thing I didn't stress when I was describing the sequence instructions is that your patterns in memory, the bit locations, have to match the bit locations of the inputs and outputs that you want to deal with. Okay? So, let's make that happen. All right, so here's my list. I can make it smaller so it's out of my way. Pull this over to the side, get rid of the extra window. I don't need 2 logic screws running. And make sure we got room for that table. Good. Okay, so basically all I really need to deal with right now are the mask moves. Now, to make it easier on you, what I'm going to do is put the data into memory directly. And so let me move some things around. I guess it would be best to see the simulator itself. And let's see. And the list off to the side. Okay. Okay, so here's the heart and soul of our process. It's the valve, the motor, the level, and the prox sensor. Okay, now to make my life easier, I'm just going to clear all the data tables, clear all data files. That way, and then when I refresh it, yeah, they're all gone. Now, remember in my sequence instructions, I have the compare list, the inputs, excuse me, begin at address 1, and the outputs begin at address 11. Because remember, I have to go 1 address past what I put into the command. Okay? So I'm going to put my input lists in here, starting at address 1. And let's see, what I need first of all is a 0, 0. Check, got it. Okay? That was easy. But you have to be careful because I highlighted the wrong bits. Actually, it's bit 3 and 4 because that corresponds to input bits 3 and 4. The comparison is performed between two words of data with more of a bitwise and. The bits have to line up, otherwise it doesn't work. Okay? So I need to see that input 3 and input 4 are off. Okay. Next, I would like to see that input 3 is on. Now be careful here. I purposely put these two backwards. But this particular line of bits deals with bit 3. And this one deals with bit 4. I can't just take these and copy them over as they are because I'd have them backwards. Does that make sense? So I have to be careful. So I need 3 ones on address 3 after this. So that's going to look like the following. 1, 1, 1, 1. All I did was I copied this line in here, starting at address 1. Now I'm going to copy this line in on bit 4, starting at address 1. So I need 0, 0, 1, 0. And that's it. My inputs pattern is done. Now if I run the program, the mask moves are going to completely obliterate this. So we'll fix that in just a second. Okay? But for right now, that's the data that I need in memory that I'm going to compare inputs to. So I'm going to compare a whole word of inputs to a whole word of binary data. Now let's set the outputs. The outputs start on address 11 because if you remember, well, I won't show it to you, but that's what I used in the sequence output instruction was actually address 10. I have to go one past. So let's see, output 0, output 1, I've got these backwards as well. That's fine, it doesn't really matter. But I'm dealing with bits 0 and bit 1. So let's set, what do we want? Well, we want motor on. Then we want valve on, then motor on, then motor on. You see what I did? Just copied these lists, so this list over into memory. Now this is a quick and easy way to do it. Notice that there's only 4 steps in my sequence. I don't need this anymore. I'm going to save it so that I can post it as I promised you. Save as computer. I thought they were trying to eliminate clicks. Software not have silo sequence UNCE machine. Okay, so I'll post that for you guys a little later. I'll put it in with the programs. It's off the screen. Okay. Now I'm going to work with the masked moves in order to make them work the way I want them to. I don't need 8 masked moves because I only have 4 steps in my list. So I'm going to eliminate 4 of them. Let's see, there's 1, 2, 3, 4. I'll keep those. Anything after that, I will get rid of. Okay, so I don't need these branches. Now let me rearrange these because I would rather have the inputs list first and the last. That will make more sense to you. And to keep it really clean, I'm going to change the bit numbers. Switch those around as well. Just changing some references. So here's the outputs list. It references address 11, 12, 13, 14. The input list is still too long. Once again, I only have 4 steps in my list. So 1, 2, 3, 4 instructions. There are 4 branches. That's a bit more manageable. Now, what bits do I really want to look at on the inputs? 3 and 4. So what should my mask look like? Consider that. I am not interested in bit 0. I'm not interested in bit 1. I'm not interested in bit 2. I am interested in bit 3. I'm interested in bit 4, and there are no other bits that I'm interested in. So that in binary should be my mask. What is this value in decimal? This is the ones, twos, fours, eights place. This is the 16s place, 16 and 4, 24. So my mask should be a decimal 24. Now, if you don't remember that, you should be able to type in numbers in binary. Now, a minute ago it didn't let me. Let me try again. 0, 0, 1, 1, 0, 0, 0, binary. Let me this time. I don't know why. Some of the instructions let you, some don't. Fine. But it's 24. Do you understand why it's 24? Any questions on it? All of these masks will be 24 because the only two inputs I'm ever interested in looking at are bits 3 and 4. Now, what do I want to see? Well, here's where I'm going to cheat just a little bit and save some time. I've already programmed in the bits. I don't want to go and compute the decimal value of all these. I'm going to let the software do it by hitting decimal. I want to look for 0, 8, 24, 8. Does that make sense? So it's very easy to put 0, 8, 24, 8. And what that will do is it will copy 0, 8, 24, 8 into these memory locations just as they are. Because notice I'm referencing address 1, which is this one right here. Address 2 for the 8. Address 3, which is where I get 24, which is address 3. Sure enough, if you look, that is 24 for address 3. But Logix Pro likes to switch back to binary view. And then finally, address 8. Or I'm sorry, number 8. So that's my list. Now I have not set the mask moves up for the outputs list, but the output list will just be 1, 2, 1, 1. Now I'm going to let you guys help me a little bit more. What should my mask look like? Should it be 15 or something else? I'll give you a hint. I'm looking at the outputs. What output bits am I interested in changing?
The motor and valve.
That's right. What are those bit numbers?
0 and 1.
That's right. If both bit 0 and bit 1 are on, what's the decimal value of Y1? 3. That's right. Everybody follow that? It can be confusing because, I don't know if I can move that back. I don't know how to do that. It can be confusing because, look, in decimal, we're just putting a 1, 2, 1, 1 in. So you may be tempted to say, well, the biggest number is a mask. That's not really the case. Because notice there's never a time where both of the bits are on. If both bits are on, we would get 3, and we would see that, sure enough, we need a 3 as the mask. But they are never both on. But we still want to affect both bits. Because in these mask moves, we want to intentionally turn bits off as well as turning them on. Okay? So the pattern was what? 1, 1, 2, 1, is that right?
1, 2, 1.
Yeah, 1, 2, 1, 1. So 1, 2, 1. We got lucky that it was almost right already. Okay. Now, I claim that barring any other mistakes that I've made, this program should simply work. It should simply start filling boxes once I hit the run. Let's find out. Let's download, run it. Now before I hit start, I'm going to go into memory and make sure my lists are still as I expect. If I can get there. Can't see these up here, but these down here look right. I'm happy with that. Now as soon as I hit the start button, that should seal in the circuit, which should activate these sequence instructions, and it should start working. And it didn't. Wow.
Here, on line 3, you didn't put your motor in.
Actually, what happened is, notice I did not seal in with the appropriate bit. I forgot to change this address to 2/2. Okay. Let's try again. Now, unfortunately, notice that the sequence compare and sequence output have advanced, so I have to somehow correct those. I'm going to simulation, clear all data tables. That will blow away all the binary bits in memory. That's okay, because I've got max moves that are going to recreate it. But that will reset the registers as well. So run, Did it reset? Let's start.
I don't know if you can download it.
May not have.
You gotta run it.
Anxious?
Very much.
Oh, you know what happened? These bits were set before in memory. And so, well, no, the data is correct. So one more time. Clear all data files and pages. Okay. Download, run, start. Run is finally on, but it's not doing what it's supposed to do. It's time for a break anyway. Let me figure out, because I made a simple mistake or something. Let me just find it. Oh, I found it. That was dumb. I'll tell you when we get back.